Hello everyone, welcome to my presentation on the Beijing Air Quality Analysis and Prediction System built with Python and Streamlit. This work uses data-driven methods to study and forecast pollution levels in Beijing. It brings together data analysis, machine learning, and web app development. I'm Faisal Ahmed, and this is for my data analysis module. Let's start with the issue at hand. Air pollution is amongst the biggest environmental problems we face today. Dangerous substances such as particulate matter and toxic gases threaten both human health and the environment. Millions around the world suffer from poor air quality, especially in crowded cities. We urgently need better monitoring and forecasting systems. Without them, we cannot warn vulnerable communities or assess whether government actions are making efforts. Now let me explain why PM2.5 is so harmful. PM2.5 refers to tiny particles measuring 2.5 micrometers or less across. For comparison, these particles are about 30 times thinner than air. Stand of human hair. You cannot see them, but they are everywhere. Is polluted. Yeah, what makes them dangerous? Because they go deep into the lungs, escaping the body's natural defenses. Second, they move into the bloodstream and circulate throughout the body. And third, they get around the filtering systems that usually protect us. Beijing has struggled with serious air pollution for the last 1 years. Table 1 highlights four main causes. First, fast industrial growth has released more emissions from factories. Second, more vehicles on the road have raised NO2 and CO levels. Third, city expansion has increased the need for energy. Fourth, burning coal for power has pushed up SO2 and PM2.5 levels. The good news is that government actions, including the Air Pollution Prevention and Control Action Plan launched in 2013, have brought improvements. Let me now share what this project aims to do. I have built a data-driven system that performs 4 key tasks. It looks at Beijing's past air quality records to understand pollution trends. It finds connections between pollutants and weather factors. It creates models to predict PM2.5 levels, and it offers an interactive tool where users can explore the data and run their own predictions. The ultimate goal is to turn raw numbers into practical insights that can help protect public health. To meet this aim, I set 5 clear objectives. First, gather and combine data from several monitoring sites. Second, carry out exploratory data analysis to discover hidden patterns. Then build and test machine learning models and predict PM2.5 levels. Fourth, create a user-friendly Streamlit application that makes the analysis easy to use. Fifth, manage the project development using GitHub for version control. Let me tell you about the data I worked with. The source is hourly air quality readings from 12 monitoring stations across Beijing, recorded between 2013 and 2017. That is more than 4 years of continuous data. The dataset includes the measurements of 6 different air pollutants and 5 weather-related variables. Altogether, I have tens of thousands of hourly records, giving me a strong foundation for analysis and model training. For comparison purposes, I picked 4 stations, as table 2 shows. The urban stations are Dongji and Guangyuan. Dongji is a busy area with dense population and heavy traffic. Guangyuan is affected by industrial sources and city activity. Table 3 lists the suburban stations, Shuni and Heru. Shuni has a relatively low uh, population density. Heru has fewer pollution sources and generally cleaner background. Yeah. This slide presents all the variables in my dataset. Table 4 lists the pollutants, PM2.5 or fine particles, PM10 or larger particles, SO2 or sulfur dioxide, NO2 or nitrogen dioxide, CO or carbon monoxide, and O3 or ground level ozone. Table 5 shows the weather variables, temp for temperature, for pressure, DEWP for dew point, and WSPM for wind speed, and rain for rainfall. Together, these 15 variables makes up the complete data set for my analysis. Task 1 focused on getting the data ready. Step 1 was importing the data using pandas to read CSV files. Step 2 was combining the data by adding a station column and merging all data frames. Figure 2 shows a preview of the March dataset. Step 3 was creating a datetime column by combining year, month, day, and hour fields. The final result was a clean time index data frame ready for analysis. Task 2 was exploratory data analysis. The data has several features. It is large-scale time series data, includes both numbers and categories, and has some missing values. I cleaned the data by removing duplicates and using forward fill to handle new sync entries. The statistical summary showed three main findings. PM2.5 varies widely, extreme pollution levels exist, seasonal patterns are present, which led me to dig deeper with visual analysis. First, I looked at single variables. The PM2.5 histogram shows a right skewed pattern. This means most readings are at lower levels, but there is a long tail reaching out to very high values. This tail represents pollution spikes or severe events. This pattern confirms that Beijing generally has moderate pollution days, but occasionally experiences dangerous episodes. Next, I examined relationships between two variables as Figure 5 shows, PM2.5 and temperature having weak negative link. Colder weather tends to come with higher pollution. The reasons include more heating emissions in winter and temperature inversions that trap dirty air. The relationship between NO2 and O3 is clearly opposite. This happens because of complex chemical reactions where NO2 can both create and destroy O3 depending on sunlight. Then I looked at many variables together using a correlation heat map shown in Figure 6. I made a key fix. I selected the numeric data types to avoid errors. Table 6 summarizes what I found. PM2.5 and PM10 have a strong positive link, meaning they come from similar sources. PM2.5 with NO2 and coal have a moderate link, pointing to combustion sources. PM2.5 with weather variables have only a few link. Figure 7 shows a box plot comparing PM2.5 levels across stations, as Table 7 shows. Urban stations like Dongzi and Guangzhou higher pollution levels and more variation. Suburban stations like Shuni and Heru have lower levels and more consistent readings. This confirms that people in cities face greater pollution exposure. The time series analysis reveals that winter months see the highest peaks, while summer has the lowest readings. Task 3 was building a prediction model. I choose random forest for this job. Table 9 explains why. First, it can handle nonlinear relationships between variables. Second, as an ensemble method, it reduces overfitting and works well with different types of data. Third, it tells me which features matter most. I use scikit-learn with 100 decision trees for evaluation. I used R2 score to see how much variance and the model explains, and mean absolute error to see the average prediction mistake. Task 4 was creating the Streamlit application. This is an interactive web dashboard for exploring data, viewing charts, and running predictions. Table can list 6 pages. The dataset page shows a preview of the raw data. The overview page gives summary statistics. Missing data info and correlation heat now. A visualization page lets users create histograms and scatter plots. The station comparison page compares urban and suburban PM2.5 levels with box plots. The time series page shows daily pollution trends over time. Task 5 was using GitHub for version control. I created a repository and made regular commits as I developed the project. For example, I committed messages like build Streamlit app or dataset and other pages. The benefits include being able to track changes, keep the project organized, and get ready for future teamwork. Even though I worked alone, the setup is ready for collaboration. Let me give a balanced assessment of my project. The strength are thorough EDA covering 3 types of visual analysis, strong model performance from random forest, and an interactive application that makes the analysis easy to use. The weaknesses are only use the variables provided to external factors like traffic or industry data are missing. I handled missing data simply with forward fill instead of more advanced methods. The model is not valid. It only works on past data. Table 11 lists future improvements using LST networks would better capture long-term patterns. Adding live data feeds would enable real-time forecast. Deploying online would make the app accessible to anyone. Improving the interface would give a smoother user experience. In conclusion, I have shown how data science methods can be used to study and predict air pollution in Beijing. The main achievements are for first, I combine data from several stations into one unified dataset. Second, my EDA revealed clear differences between urban and suburban and areas plus strong seasonal patterns. Third, I built a well-performing machine learning model that predicts PM2.5 levels. Fourth, I created an interactive Streamlit app that makes these tools available to people without technical backgrounds. Then I have a few references here. If there's any questions, I leave my name and email address here. Thank you for listening. Thank you for watching.